In this video, we're going to explore how we would interpret derivatives, and specifically partial derivatives, when we have a function of multiple variables in an application context. We're going to start with an economics example. If you imagine G is the amount of gas sold per week by a gas station, and X is the price sold at your current gas station for the gas, and Y is the price charged by a competitor, imagine what these partial derivatives would have in terms of their sign. Again, signs of derivatives are one of the most important features of them because they tell us how different variables relate. And just as a reminder, if we're talking about the derivative of G with respect to X, the way to imagine the influence of that, or the sign of that, is to ask, if you increase X, what happens to G? And likewise, when you increase Y, what happens to G? That captures the sign of the partial derivative of G with respect to Y. So take a moment, think about these scenarios, translate these into the context of the gas station problem, and then we'll check in on the answers. All right. Well, if X is the station's price for gas, our own price, we know that if X increases, or our price increases, we can expect G, the sales, to decrease. And if that's the case, the derivative of G with respect to X, there's a partial derivative in both cases here, I'll try to make that more explicit, this is going to be negative. When X goes up, when our price goes up, G goes down, our sales go down. In contrast, if Y is the price charged by a competitor, in other words, the person that is also selling gas, if our competitor price increases, if shoppers have a chance to view that and compare, they're going to come and buy more from us. And so our sales, that's the key thing, G is still all about us, is going to go up. Our sales are going to increase, and so this derivative G with respect to Y will be positive. So we're looking at option C out of the catalog here. The analysis, though, comes always down to the same process. If we were to increase the variable X, that's going to give us information about the partial derivative of G with respect to X. We just need to figure out what the consequence is in the scenario. And we just repeat the same idea for Y. Let's imagine a different scenario here where we have H being defined as the number of pairs of ski lift tickets sold in a year. X is the number of ski boots sold, and Y is the number of tickets from Canada's warmer vacation spots. Take a moment to draw out those scenarios where we have X increasing and Y increasing, and what those mean for H. You can pause the video and then we'll check in. All right. Well, if X is the number of ski boots sold, we expect that that's going to be correlated with lift tickets sold because people don't tend to buy. If we increase the number of boots sold, it's because people are going to go and ski in them. And so what we'd expect to see here is an increase in H. And so a positive relationship here between boots sold and ski lift tickets sold. If we talked about tickets to warmer vacation spots, though, typically if people are spending more on their vacation south, then they're going to spend less on ski resorts and ski trips. And so what we expect to see here is a negative relationship, a negative derivative of H with respect to Y. And so what we're looking for here is option B. For those who have done some economics, what we'll be looking at here are ski boots and ski lift tickets are complementary purchases, whereas vacations to ski resorts versus vacation to warmer spots are substitutes. We can do one or the other, but we would likely not do both. So there's a nice theory that goes in behind this on the economic side. For our purposes, though, the analysis we're focused on is being able to conjecture what happens if we increase one of the variables, specifically to the outcome of our function variable here, H. If we increase X, what happens to H, and how do we interpret that as a rate of change?